We're going to talk about the integrated rate law next. Now, the integrated rate law is what you get when you take the definition of rate and you take the rate law and integrate them over time. So really, calculus, I'm not going to make you do calculus. We're going to use the outcome of this to do some calculations. Now, I also have some graphs here. The goal of the graphs is to help you understand what the different orders mean in terms of how rate depends on concentration and how concentration changes over time. I will generally not ask you to recreate these. So just an early warning, this is here to help with understanding. For zero order reaction, remember for our rate law, the rate was equal to the rate constant. So if we're looking at a plot of rate versus reactant concentration, the rate in molarity per second stays the same regardless of the concentration. So we just have this horizontal line. If you look at the reactant concentration versus time, we start at some concentration and then it just goes down at a very regular slope. I guess that's the way I want to say that for this, right? Our reaction is just chugging along at some constant rate. So my concentration is just going to go down as the reaction proceeds in a very linear, predictable fashion. For a first order reaction, so rate is equal to the rate constant times the concentration of A, right? First order dependence on A. The rate versus the concentration of A. So first order dependence means that it's just this directly proportional to A. As A increases, the rate increases in the same way. So I have positive slope, linear relationship between rate and concentration. So looking at the concentration of A versus time plot, now as my reaction happens, the concentration of A goes down. But as the concentration of A goes down, my reaction goes slower. So then my concentration of A does not go down as quickly, but it still goes down, so then my reaction goes slower. So then it doesn't go down as quickly, but it still goes down, and then my reaction goes slower. So you get, right, just kind of back and forth. You get this kind of tapering off effect in the concentration versus time. It will start to disappear more slowly as the reaction proceeds because the reaction is slowing down. For a second order dependence, rate equals K times concentration of A squared. Now I have an X squared dependence. So the increase in a concentration will have a more drastic effect on the rate. Well, this translates to, when we look at concentration of A versus time, that the concentration of A going down has a bigger effect on the rate. So we still get this tapering off effect, but it's much more pronounced. Okay, integrated rate law. So now we're going to show a relationship between concentration and time. So as I mentioned, it brings together the rate law and the definition because they're both the rate. So they are set equal to each other and then integrated. So you have to know the rate law in order to use the correct equation, because it will be a different equation for zero, first, second order, and so on. These equations are labeled on the equation sheet. So it does say which is for 0, which is for 1, which is for 2. So those can be the only ones I give you because those are the only equations that I give you. For 0 order, what this looks like is concentration of A at time t equals negative KT plus concentration of A. The 0 just means the initial concentration. So my concentration at a specific time depends on the rate constant, how long it's been, and the initial concentration. This should look like a linear relationship. That's what we graphed. For first order, the natural log of the concentration of A at time t is negative KT plus the natural log of the concentration of A at time 0. So there is another way that you can write this. I think I give you this written out form, but remember that with addition and subtraction for natural logs and logarithms, you can go in and out of division and multiplication using this. So this could be rewritten as the natural log of concentration of A at time t divided by concentration of A at time 0 equals negative KT. So this may be the way that you have to use this depending on the information that you have. So as an example, right, I have concentration of A at time t over concentration of A at time 0. I have this equal to 0.75. So this is what you would write if, for example, you were told that 75% of A is left over. Or if the reaction runs until 25% of the A has been used up. So the A at time t is the remaining 0.75 relative to the 1, or 75% relative to the 100% that you started with. For second order, it has this 1 over concentration dependence. Right, again, these equations are given to you. This also, right, we've got some weird like 1 overs and some weird natural logs. This is another way that you could find the rate constant. So I am not going to ask you to do this, but just so that you know that this is a thing that could be done. The way that these are formatted, these integrated rate laws, these should all make straight line plots. For 0 order, if you do concentration of A versus T. For first order, if you do ln of A versus T. And for second order, if you do 1 over A versus T. In the case of 0 and first order, when you plot this data, you have a negative slope, so you have to take the opposite of it to get K. But for second order, since we're plotting 1 over, and you start with a high concentration of A, which means 1 over A is small, go to a small concentration of A, so 1 over A is big, you get a positive slope here. So the slope is just equal to the rate constant. All right, so how do we even use this information? The way that we will use it is like in this example. So we have the decomposition of a molecule. That decomposition is first order, and we're given the rate constant. And we are asked, what is the concentration of SO2Cl2 at time equals 865 seconds if the initial concentration is 0.0225 molar? So we have to know the order so that we choose the equation that has the correct concentration dependence in order to find out concentration at a later time. So integrated rate law, it's the relationship between how much is left, depending on how much you started with, given the constraints of the law that controls the rate of this reaction. So it kind of puts everything together in one equation. So this is first order. So I'm using the natural log of the concentration of A at time t equals negative KT plus natural log of the concentration of A at time 0. So I'm just going to start by putting in here the things that I know, not even the numbers, but concentration of A at time t, what does that mean? for the reaction I'm looking at. What that means is the concentration of SO2Cl2 at 865 seconds. That's what I'm looking for. And on the other side, natural log of concentration of SOCl2 at time 0. So that's whatever my initial concentration was. I don't have to rearrange because I'm looking for the concentration at 865 seconds. I do plug in the rate constant, so the natural log of the concentration at 865 seconds is equal to negative times the rate constant, so 2.90 times 10 to the minus 4th 1 over seconds, times 865 seconds, plus the natural log of 0.0225. And I've got natural log underlined like 3 times on here. Don't forget that the natural log is there. It's vital to getting this calculation right. So the natural log of the concentration at 865 seconds is equal to negative 0.251 minus 3.79. So the natural log of that concentration is equal to negative 4.04. And if I want to get something out of a natural log, the way I do that is doing both sides up to the power for e. So e to the natural log of the concentration of SO2Cl2 is equal to the concentration of SO2Cl2, and then e to the negative 4.04 will just give me a number. So e to the negative 4.04 is 0.0175 molar. So the concentration of SO2Cl2 at 865 seconds is 0.0175 molar. I can check to see if this makes sense. Right, intuitively, first order, second order, zero order may or may not be able to gauge it too well, but our reaction proceeded, the reactant should go down. You can check that, and we do have that. So my concentration went down as the reaction proceeded. Fantastic. The other thing that we do with this integrated rate law is talk about half-life, which the half-life, we label it T1/2. It's the time required for the concentration to reduce its initial value to half of what it was when it started. So that's the definition. Concentration of A at time t is 1/2 of concentration of A at time 0. That, if you take that equation that I've written and plug it into the integrated rate law, that's where all these other equations come from. However, right, I'm not going to ask you to derive them. I will give you these half-life equations. What you need to know is that it does depend on the order of the reaction. And like, why half? Like, why are we picking this specific concentration point? I mean, why not go like 99%? Like, when is it 99% gone? Really, half, if you know what you started with, just figuring out the half-life gives you some of that information. Some half-lives can be really long, and we tend to talk about half-lives when it comes to chemicals that are dangerous, or how long chemicals will stay in your body, or something along those lines. So we've just picked a consistent point across everything that can help us monitor for good or bad how those concentrations are changing over time. The point that we picked is the half-life. So the equations that you will see for zero order, the half-life is the initial concentration divided by 2 times the rate constant. So for a zero order reaction, the half-life depends on the concentration of A, and the half-life gets shorter as the concentration of A decreases. So zero order, right? This reaction is just going at a specific rate. There's no change to the rate of the reaction as the concentration changes. So the amount of time that it takes will depend on the concentration that you start with. So if you start with 1 molar and it goes at some constant rate, that time to get to 0.5 molar, it just depends on the fact that it was 1 molar to begin with. For a first order reaction, the half-life is 0.693 divided by the rate constant. So this seems weird, but just remember we're talking about half-lives and not rates. So first order, there is a dependence on concentration, but for the half-life, there's no dependence on concentration. This gives us constant length half-lives. So something like caffeine in your body is eliminated by first order kinetics. It doesn't matter how much you consume, you will cut that amount in half in predictably length units, right? Whatever the length of the half-life is, if you consume 800 milligrams of caffeine in one half-life, you'll go to 400. If you consume 600 milligrams of caffeine, in one half-life, you'll go to 300, but that's in the same amount of time. So, okay, first of all, please don't consume either of those amounts of caffeine in one sitting. 600 is probably a high limit for one day. It's probably an excessive limit for some of you. It might be what I get close to having in a day. That's kind of frightening. But it doesn't matter how much you have. If two separate people had those different amounts of caffeine, it would be cut in half in the same amount of time. For second order, you do see a dependence. The half-life is 1 over the rate constant times the initial concentration. This one's like, you really hope that something doesn't go by second order kinetics. If it's not good for you, the half-life gets longer as the concentration of A decreases. So as it goes down, it takes longer to go away. And that's because it has such of a strong dependence on the concentration in the rate of the reaction. Okay, let's do a plot of this so that you can see what it looks like. I'm always happy to talk about half-lives and medications especially, or things like caffeine or ethanol, and how that affects the way that our bodies react to them. But what I will give you first, and for this video, is just a graphical representation of what we're talking about. So for a first order reaction, if we're looking at concentration in seconds, you'll see that this plot is going to start to look like the one that I drew at the very beginning, and it should, because of what half-lives tell us and how they're related to the rate of a reaction. So I'm going to do a plot. Initial concentration is 1 molar. The half-life is 100 seconds. So in one half-life, in the first 100 seconds, my concentration will go from 1 molar to 0.5. It will be cut in half. Now, in the next 100 seconds, I'm starting at 0.5 molar. In the next 100 seconds, my concentration will go down to 0.25 molar. In the next 100 seconds, it will go from 0.25 to 0.125. So every half-life, the concentration is cut in half. This is a first order reaction that I've plotted here, which is why my half-lives are all the same length. So 100 seconds for the half-life. For a first order reaction, the half-life is not concentration dependent, and that's why it's plotted here.